Salam and hi everyone. So let's proceed with our topic 2 here in number systems, SKEE1223 digital electronics. So this is the outline of this week's topic. Basically this week we're going to cover number systems, covering binary numbers and its conversion from decimal to binary. Okay, and then we also have hex numbers. We have the octal numbers. We're going to look a little bit on the gray coding, ASCII characters, and Unicode characters. So as a basic, what does it mean by binary, and how do we count in binary? So as you've seen in the introduction, when we talk about digital systems, it's either the computer understands either a 1 or a 0, where a 1, for example, 3 volts on the wire or on the node, you have 3 volts, logic 1. If it's ground or 0 volts, we consider it as a logic 0. So binary means two systems, binary. So in binary system, we have a digit has only two values, either a 0 or a 1. So for example, here in this table, if we want to represent the number 0, we can use a one bit, okay, one bit or one value or one wire, where you can give a value of 0. If you want to represent the number 1, we can give a VDD or a voltage supply on the line where we say it's a logic 1. Now for number 2, since binary is only allowed 2 digits, 2 possible values, which is 0 and 1, so number 2 has to be represented using 2 bits. Okay, so these are the bits here, so bit 1 and bit 2. And for number 3, we also need to use 2 bits, and 4 here, we're going to need 3 bits. Okay, so counting in binary, we start with 0, 1, and the number 2 is 1, 0, number 3 is 1, 1, number 4 is 1, 0, 0, 5, 1, 0, 1, and so on. We'll see more details later on, how we can derive the binary, how we can get the binary equivalent from a decimal number, and how we can also convert a binary into a decimal. Okay. Okay, so let's proceed here. So as an example, we find the decimal value of 0010. So this is in binary or base 2. So we want to find what is the equivalent decimal value. Okay, the value that we understand, the human understand, the decimal value of 00101. So from here, the method is basically, this is your binary number. Okay, 00101, and what we do is we're going to multiply by the base to the power of the bit position. Okay, so here is a base 2, so 2 to the power of the bit position, so 1 times 2 to the power of 0, plus this is 0 times 2 to the power of 1. Okay, for the 1 bit position, so this is position 0, 1, 2, 3, and 4. And for each position, we are going to sum up the bit position multiplied by the base, okay, to the power of the bit position, and the sum of all that will give you the decimal value 510. Okay. And if we are given a decimal value, okay, 650 is a value that we understand. Okay, 650. And how to represent that in terms of binary, in terms of 1 and 0s. So the method here is using what is called a repeated division method. So how does it work? Basically, we are going to start with the original value here, 650, divided by 2, because we want to convert to binary. Okay, later on we'll see that actually this number can be different number. Okay, for example, the hex is divided by 16. Now we want to convert to binary, which is a 2-valued number. So we divide by 2, and the quotient here, so 650 divided by 2 is actually 325, okay, with the remainder 0, we put a 0 there. 325 we bring here, divide by 2, we get 162 with the remainder 1. Okay, so we just complete the table, 162 goes down here, 81, and so on until we get the quotient 0. Okay. So when the quotient is 0, so 1 divided by 2 is actually 0 and remainder 1. Okay, and after that we cannot we cannot do any further. and therefore your solution here is actually from down to up. Okay, so your solution is 1101 going up, so you can see here, so 101 000, so 101 000, and so on until the end. So therefore 650 base 10 is equivalent to 101 000 1010 in binary or base 2. Okay, so some examples here. Let's have a look at some examples. So given 1010 base 2, okay, binary, how to find the equivalent decimal? So what we do, remember, what we do here is, this is a bit position. So this is bit position 0, bit position 1, bit position 2, bit position 3. And we see here that bit position 0, 0 and 2, we have a 0. Okay, so we have a 0 value in position 0 and 2. Therefore, your answer here is just going to be 1 times 2 to the power of bit position 1 plus 1 times 2 to the power of bit position 3. Okay, so this is position 1, position 3. And here you have 2 plus 8, which is equals to 10 in base 10. Okay, base 10 or decimal. So that's why you get 10 here. Okay, similarly here, we can see that is 2 to the power 4. So this is bit position 4. Okay, 0, 1, 2, 3, 4. So 2 to the power 4 plus 2 to the power of 2. Okay, notice here there is no 2 to the power of 3 because 2 to the power of 3 is 0. Plus 2 to the power of 2 plus 2 to the power of 1 is this one. And plus 2 to the power of 0 is this one. And if we sum them all together, we are going to get 23. Okay, so convert the decimal numbers to binary. So here we use a repeated division. So again, we're going to start with 19 base 10. Okay, 19 base 10. So what we're going to do is we're going to divide by 2. Okay, so 19, okay, so the first value, okay, we have the quotient and the remainder. 19 divided by 2 is actually 8. Okay, sorry, 9. Okay, with remainder 1. 9 divided by 2 is 4. Okay, remainder 1. 4 divided by 2 is equals to 2, remainder 0. And then 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. And then we go up here. Okay, and we see that we're going to get 1, 0, 0, 1, 1 base 2, which is 1, 0, 0, 1, 1 base 2. Okay. So similarly with 58, so you can do the same. I'm not going to show here. So if you do the same, 58, but 58 we can also see another method here whereby you can see that 58 is a combination of the power of the bit positions. Okay, so for example here, 2 to the power of 5 is 32 plus 2 to the power of 4 is 16 plus 2 to the power of 3 is 8 plus 2 to the power of 1 is 2. So this is actually equals to 58. Okay, so so this 58 corresponds with bit position 5, 4, 3, and 1. Okay, so this is 5, 4, 3, and 1. Okay, 0, 1, 2, 3, 4, 5, 4, 3, 1. Okay, so that's another method that we can get from binary to decimal. Okay, so let's proceed. Common bit groups. So commonly, if we say a 4-bit value, for example 1011, which is 4 bits, we're going to call this a nibble. Okay, so we have a 1 nibble, 1011, and if we have an 8-bit value, let's say 10110011. Okay, this is 8-bit, and we say this is 1 byte. Okay, so this is a 1 byte number, and if we have a 16-bit binary, we call it a word. If we have a 32-bit binary, okay, we call it a double word, D word. And if we have a 64-bit binary, we call it a quad word. So these are just some terminologies that they use. This is standard for Intel PCs. Okay, so Intel, but ARM CPUs, for example, they consider 32-bit as a word. But this is our standard here, that 16-bit is a word. So given a binary number, okay, let's say 1 nibble or 1 byte, what is the largest value that you can represent? What is the range or the largest value that you can represent given a certain number of bits? So for example, if you have 1 bit, okay, 1 bit is either 0 or 1, Okay, so the largest value is 1, okay, which is 0 or 1. And then if you have 2 bits, okay, 2 bits, so 2 bits you can consider 0001, 1011, so 4 possibilities, and this is number 3. Okay, so 0, 1, 2, and 3. So the largest number that you can represent for 2 bits is just 3. Okay, and the range is between 0 to 3, 0 to 1, okay, and then 0 to 7 for 3 bits. So if you have 32 bits, what is the maximum number that you can represent? Is in fact 2 to the power of 31. Okay, so 2 to the power n minus 1. Okay, for example, here is 2 to the power of 0. We get the maximum number. Okay, let's look at the hex number. So hexadecimal here means 16. Hexadecimal means 16. In the hex system, a digit can take the value of 0 through 9, A through F. Hex is used to write binary numbers in a compact form. Okay, so as you can see here, a binary value of 000, a decimal equivalent decimal of 0, a hex value of 0. Okay, let's look at the example of 0111. So remember 0111, we have 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2. So that's 4 plus 2 plus 1, which is 7. Okay, in hexadecimal is also 7. Okay, and let's look at another example of a B here. What does it mean by B, a value in hexadecimal? So a B here means a decimal 11 or a binary of 1011. Okay, so it's in fact 11. Okay, so 11 in decimal is equivalent to a B in hexadecimal. Okay, let's look at some examples here on the hexadecimal number conversion. So let's say you are given this binary, okay, 10110110110001 in binary, and you are asked to find the equivalent or convert this binary into a hex number. So what do? You start with the LSB. Yeah? So here is called the least significant bit, or the LSB. Okay, and here is called the MSB, most. Here is most. Okay, most significant bit. So we take from the least significant bit, and we're going to break it into 4. Okay, into 4 groups of binaries. So here is the first group. Here is your second group. Okay, remember from the LSB to the MSB, the third group and the fourth group. Okay, and what is the hex value, okay, of the group? So here is 1001 is actually a 9. Okay, looking at the table up here. Okay, given a certain binary value, what is actually your hex value? Okay, so what is 1101? What is 1101 in hex? It's actually D. So how do we know that? We're going to look here. 1101 is in fact equals to D. Okay, and 0110 is a 6, and here is 0001. Okay, we are going to expand to 0 at the end there. This is in fact 1. So here is the equivalent hexadecimal for this particular binary. And also remember that we can also find the equivalent decimal number for this particular binary, which is quite difficult to do. You need to count the bit position and so on. Okay, so let's look at the conversion here, hexadecimal to decimal. So convert the following to binaries. So given CF8EE base 16. Okay, so base 16 there we know that is actually a hex value. Sometimes written like this, 0x CF8E. Okay, if you have 0x there, it also means that it's a hexadecimal value. So what we do is we're gonna break into groups. So this should be E. Okay, this is your E value, this is your 8 value, this is your F, and this is your C. Okay, based on the table we saw just now. So this is CF8E, and then what about 974 base 16? So this is 4. Okay, this is 7, and this is 9. So 974 base 2. Convert the following to hexadecimal. So given the binary, so this is A. Okay, this is 0, and this is F, this is 9, this is D, this is 1, and this is 2. I'm going to extend here. Okay, 0010 is a 2, so we get, this is the answer. Okay, 21D9. Okay, more number conversion. Convert A7B16 to binary and decimal. Okay, convert A7B16 to both binary and decimal. So what we do is we're going to take A7B. So binary. Okay, so let's have a look at this example here, where we want to convert A7B base 16 to binary and decimal. So we have the A7B. Okay, so one way is to convert to binary first. So how to convert this to binary? So A is actually 1010. Okay, 7 is 0111, and B is 1011. So this is base 2. Okay, here is base 16 in hexadecimal, which is equals to 2 to the power of, and now we have to count the bit position. So this is 2 to the power of 0, 1, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it's actually 2 to the power of 11 plus 2 to the power of 9 plus 2 to the power of 6 plus 2 to the power of 5 plus 2 to the power of 4 plus, and so on. And we should get, if you do the calculation correctly, we should get a decimal value of 2683 base 10. Okay, so these are all equivalent: base 16, base 2, and base 10. Okay, so convert 65010 to hexadecimal. There are two ways. So if you have a 65010, how to convert to base 2? Okay, so remember we do a repeated division, 650 divided by 2 and so on, and we get some binary. And once we have the binary, we can use this method to break up the binary into 4 groups each and get the hex. But there is a simpler way where we can convert the 650 base 10 directly to hex. So let's have a look. So what we do is we use a repeated division, where now we divide by 16. Okay, and we get a certain number 40 as our quotient, is our Q, and we have a remainder of 10. Okay, remainder of 10, and 10 in hex. Okay, 10 base 10 is equals to A in base 16. Okay, so this is our remainder, and we are going to take 40. Okay, we're going to take 40 divided by 16, 2.5. Quotient is 2, remainder is 8. Okay, and we're going to take 2 here, bring it down here, divide by 16, 0.125, quotient is 0, remainder is 2, and therefore we already achieved 0. Okay, as our quotient, going to stop, and therefore our solution is 28A. Okay, 28A base 16, so we don't have to convert to binary first. Okay, let's look at the octal number. So octal here means 8. Okay, quite obvious. Octal means 8. In octal number system, a digit can take the value of 0 through 7. So the maximum digit or number that you can take is from 0 to 7. You cannot take the value of 8. Okay, and this is the equivalent binary, and this is the equivalent decimal. Let's see the conversion. So given your binary here, 1, 0, 1, 1, and so on in base 2. So how do you represent this in base 8? How do you represent this in base 8? So what you do is you want to break into 3 groups. Okay, break into 3 groups from the LSB. Okay, least significant bit to the MSB. Okay, and if you have extra here, you want to put 0 in the front. Okay, so 001 is 1, 010 is 2, 1117, 0113, 001 is 1, and therefore your octal number equivalent is 13721 base 8. Okay, so let's see some examples here. So 25. So 25 base 8. Okay, 25 base 8. How do you represent it in binary? So what we do is we want to break it up, right? Okay, so 5 is 101. Okay, and then 2 is 010. Okay, so that's why we have a 10101 base 2. Okay, so break up into 2 parts. 140 base 8. So 140 base 8. So here is your 0, here is your 4, and here is your 1. Okay, so 140 base 8. Convert the following to octal. So given a binary, so how do you get your octal from a binary? So it's quite simple. You just have to divide or separate out into 3 parts. So 100 is 5, 110 is a 6. And here is the same. So you have 4 parts there. This is a 1, this is a 7, this is a 5, and this is a 1. So 157, 1571 base 8. Okay, so we're done with the 3 numbers. So as a summary, we have that you need to know is decimal, which is obvious, what we know. You have the binary base 2, you have the hexadecimal base 16, and you have the octal base 8. And now we go into BCD. So binary coded decimal is a 4-bit binary, okay, from 0 to 9, which is similar to a normal binary. And let's look at gray code now. So gray code. So what is gray code? So gray code is, the idea is only 1 bit change. Okay, only 1 bit change. Okay, only 1 bit change from sequence. Okay, so for example here, if 000 is the equivalent in gray code is this. Okay, 001 in binary is the same. 001 also in gray code, but however, for number 2 in binary, we already seen that this is 2 to the power 1. Okay, so in binary is 0010. However, in gray code it's actually 0011. So we need to tell the computer, are we representing the bits as a binary or as a gray code? So if you say you're representing as a gray code, then your value of 2 is actually 0011 and not 0010. Okay, so here we can see there's only 1 bit change. Okay, 01 here is only 1 bit change, and here we have 2 bit change. Okay, the 0 change to 1 change to 0, the 0 change to 1, and here 1 maintained. Okay, let's see, going from 2 to 3, we see only a 1 bit change. Okay, 1 to 0, this one maintain, and here also we have a 1 bit change, but the idea is 1 bit change as we go from one sequence number to another. And the reason for this is for low power. Okay, for low power, less switching. Okay, so if you have less switching, we will have a low power system. Okay, so let's move on here. So given a binary number, can we convert into a gray code? Okay, for example, just now we saw that 0010 in binary is actually 0011 in gray. So how do you convert a binary to gray, or how do you convert gray to binary? So the formula is, if you have a binary, okay, here this is your gray code. So what you do from left to right, add each adjacent, so from MSB, so this is your MSB, so this is your LSB. So from left to right, add each adjacent pair of binary code, discard the carry. So here we are going to take 0 from binary, transfer 0, and we're going to plus this one together. So this plus this equals to 1. 1 plus 1 is actually equals to 0. Okay, we'll see later on. 1 plus 1 is actually 0. Then we have a carry of 1, and the sum is equals to 0. And 1 plus 0 is equals to 1. So this is your equivalent gray code for this particular binary. We'll see more examples later on. So how do you convert gray code to binary? So here is your gray, and here is your binary, and here is your MSB, here is your LSB. Okay, most and least significant bits. And now we're going to take 0 and put 0, and we are going to plus this one together. Okay, we are going to plus 1 and 0, we're going to get 1. We're going to plus this together, 1 and 1, we're going to get 2. Okay, 1 plus 1 equals to 2, but your sum is actually 0 because 2 is equals to 1, 0. This is your sum, this is your carry. Okay, so the answer is actually 0. So that's why here 1 plus 1 equals to 0. 0 plus 1 is equals to 1, and therefore this is your equivalent binary given a particular gray code. So let's look at some examples here. So how do you convert this number 10010 binary? Okay, base 2. So binary. We're going to convert this to gray code. So what do we do? So we have 10010. Okay, we're going to convert it. So 1 goes down, 1 plus 0 equals to 1, 0 plus 0 is equals to 0, 0 plus 1 equals to 1, 1 plus 0 equals to 1. Okay, and this should be your gray code. Okay, and you do the same here. Okay, you do the same there, and if you do this correctly, 110100, we are going to get a gray code of 101110. Okay, same method as this. Okay, plus. Okay, let's have a look at this one. So this is from gray code to binary. Okay, gray code to binary is a little bit different, so don't get confused with that. So this is your gray. Okay, so here is your binary. Okay, so if this is your gray, you want to convert to binary, you're going to put 1 down there, and we are going to plus this and this together. Okay, this and this together, we are going to get 0. 0 plus 0. Okay, 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. So this is your binary. Okay, so let's have a quick check here. 11001. Okay, so this is your equivalent binary. So you can do the same here. You can do the same there and get the okay, so let's leave that as an exercise, how to convert from gray to binary. And finally, we have the ASCII. Okay, the ASCII code. So ASCII is the American Standard Code for Information Interchange, and we have 128 characters represented by an 8-bit binary code with MSB 0. Okay, the 8-bit code runs from 00 to 7F. The first 32 ASCII characters used for controls. Other characters include letters, decimal, digits, and symbols. Okay, so let's have a look at example how to understand and how to read the ASCII table. For example, if we tell the computer that we have a certain binary, okay, let's say we have this binary here. Let's say D here. Let's have a look at D. So what is the representation of D in ASCII format? Okay, a character D. So for example, if I ask what is the character D in ASCII format in binary? Okay, in binary, this is your D. Okay, remember it's a 0 in the front, so it's 0100, 0100, and that's a D. Okay, in hex is 44, in decimal is 68, and you can also calculate the octal. The octal is 104. Okay, so if you tell the computer that you want to represent ASCII, then whatever binary value we give to the computer, you want to convert that into a certain ASCII character. Okay, so let's look at the example here. So if you are given AB.12 in ASCII, what is the binary value? Okay, remember the computer only understands 1 zeros. Okay, digital systems understand only 1 0, so we need to represent AB.12 in binary. So this is the equivalent binary. So how do we get this? We're going to break it into 8 bits. Okay, for example, this 2 here. Okay, this 2 there is in fact this one. Okay, so we look at number 2 in our table here. So 2 here is 110 010. Okay, so this is the number 2. Okay, and then we have the number 1. The number 1 should be this one. Okay, 011001, and then we have the dot, and we have the AB. So the A and B is I believe is this one. This is your A. Okay, and this is your B. This is your dot. This is your 1, and this is your 2. Okay, so this is the binary equivalent of the ASCII. A receiver receives the bit sequence. Okay, we got this number. Okay, from somewhere we get this hex number, which you can convert to binary, which is just going to be some value. Okay, some binary value, and we want to find what is the equivalent ASCII for this transmitted this data that you receive. So here you can see that so here you need to convert this into binary first. So for example, the B is actually 1011. Okay, 4 is 0100. Okay, so what is this in ASCII? Okay, 4B. I'm taking the last 10. What is in ASCII? So we're going to look at it should be K. Okay, we're going to look at K, and the capital K here is this one, 01001011. Okay, 01001011. So this is your T. Okay, 54. So 54 is T. So oh sorry, this is K. Okay, so this is K, this is T, this is M, and 50 here is your P. Okay, so this is a PMTK. Okay, so besides ASCII, we have also Unicode, because ASCII covers only the basic characters. Okay, for example, if you want to represent Arabic or Chinese language, Thai, or any of the letters with accents, then you need more than ASCII. Okay, you need more than 128 characters, and in this case, typically people use something called the Unicode. So Unicode have more options. Okay, let's see the example here. Examples of UTF encoding. So for example, if we want to have a $sign, $sign is represented by this is your ASCII. Okay, this is your ASCII. In ASCII is 24 hex. Okay, if you want to represent this symbol, okay, the C there, or some Korean symbols, okay, or the Euro symbol, then we need to expand more on the number of bits. And for example, the C with the slash there is actually C2A2. Okay, and that is the code for that particular symbol. Okay, that's it for our lecture for this week, and we'll continue with more we will continue more next week.